102 meters. Asterisk, asterisk. That is the average length of a modern wind turbine blade, a colossal composite structure stretching into the sky, thin enough for sunlight to glow through its edges, yet strong enough to withstand hundreds of tons of force. Yet behind that grandeur lies a question engineers have debated for more than half a century. Why always 3 blades? Why not 2? Saving millions of dollars in materials each year. Why not 20? Capturing more energy. Why does a trillion-dollar industry accept the number 3 almost like a law of nature? To answer that, we must follow an invisible battle. The confrontation between lift the force, pulling the turbine forward, and aerodynamic chaos, forever waiting to destroy any structure that lacks subtlety. In laboratories, wind is simulated using streams of blue-dyed fluid. At first, the flow glides smoothly like silk, but add just a few more blades, and the current transforms into a maze of swirling vortices, like stirring a clear glass of water too violently, where order collapses into chaos in an instant. The story of the number 3 is not a coincidence. It is a stopping point imposed by physics, a temporary peace treaty between opposing forces. As early as the Middle Ages, humans harnessed wind to turn rotating structures. Agricultural windmills relied on drag to generate large torque for grinding grain or pumping water. But that brute force mechanism does not suit the world of electricity, where what matters is not instantaneous strength, but rotational speed. When a turbine has too many blades, each new blade strikes air already disturbed by the previous one. Aerodynamicists call this broken air, a turbulent wake, filled with vortices, pressure distortions, and uneven velocity fields, unable to produce optimal lift. Imagine rowing a boat across calm water. Each stroke creates a smooth corridor behind the oar. But if dozens of people row simultaneously in a cramped space, the water becomes chaotic, reducing the efficiency of every stroke. In multi-blade turbines, this happens continuously. Every additional blade introduces parasitic drag, forcing the turbine to spend energy overcoming the turbulence it created itself. Instead of increasing power, the rotor slows down, weakening the conversion from wind's kinetic energy into electricity. Optimization, therefore, is not about capturing as much wind as possible. It is about minimizing the damage each blade inflicts on the airflow behind it. And physics begins to narrow the options. 3 blades disturb the air the least. Contrary to popular belief, wind turbines do not spin because they are pushed by the wind. They spin because they fly. The structure of a modern turbine blade mirrors a scaled-up airplane wing, an asymmetric airfoil with a more curved upper surface. As wind passes over it, airflow accelerates across the curved side, reducing pressure according to Bernoulli's principle. The pressure difference generates lift, pulling the blade forward. Crucially, this lift is not directed upward like an aircraft's. It is rotated tangentially, becoming the torque that drives rotation. Each blade is essentially an airplane trying to take off, restrained by a hub, so that lift transforms into circular motion. This mechanism demands clean, undisturbed wind. More blades mean more turbulence, degrading the quality of airflow, like a runway filled with turbulence, making stable lift nearly impossible. Too few blades create another problem. A 2-blade turbine must spin so fast that the blade tips approach local transonic conditions, where drag spikes dramatically and materials fatigue much faster. A 3-blade system achieves a golden balance between lift, rotational speed, and aerodynamic stability. It is sparse enough to preserve clean airflow, yet numerous enough to maintain continuous lift. If wind were perfectly uniform, a 2-blade turbine might remain stable. But the atmosphere is not a laboratory. Near the ground, wind is distorted by terrain, friction, and especially by the turbine tower itself. Directly in front of the tower lies an unstable pressure zone called tower shadow, air compress. slows, then accelerates suddenly as it slips past the tower's surface, like water flowing around a rock. When a blade enters this shadow, its lift drops sharply within milliseconds. It is like hitting a pothole on a bicycle you never saw coming. The entire system experiences a shock. In turbines with many blades, these force fluctuations ripple around the rotation, creating constant rhythmic impacts. But in a two-blade turbine, the problem intensifies. While one blade loses lift in the shadow, the other remains in strong wind, producing a severe force imbalance. Only 3 blades distribute these phases evenly around the rotation, allowing the turbine to absorb shocks without violent vibration. In a world where 100-meter structures spin at tip speeds approaching 300 kilometers per hour, even small shocks can become material catastrophes. When a rotating object spins, it experiences gyroscopic precession, the same phenomenon seen in a spinning top. A slight imbalance causes the entire system to tilt and rotate unpredictably. A two-blade turbine behaves like such a giant top. When one blade reaches the top of its rotation, the region of maximum lift, the other sits at the bottom, directly in tower shadow with minimal lift. This imbalance generates a tipping moment on the main shaft. The result is periodic vibration, known as chatter, mechanical oscillations that grow over time. Bearings heat up. The shaft twists. Composite materials slowly fatigue under asymmetric loading cycles. A 3-blade turbine solves this elegantly. One blade always remains in a neutral position, balancing the two experiencing extreme forces. The system's center of inertia stays stable, like a perfectly designed spinning top that remains upright despite external disturbances. The same rotational mechanics that keep a toy top standing also shape the largest energy machines on Earth. A 3-blade turbine is not a choice made for beauty. It is the only configuration that wind, materials science, aerodynamics, and rotational mechanics can all agree upon. 3 blades, a triangle of balance, have become the symbol of a new energy era.